Good morning, everyone. On behalf of the Networking and Information Technology Research and Development Program and Dr. Beagle, the program's director, it's my privilege to welcome you all this morning. I'm Bob Chaddock. I'm a program director in the Office of Advanced Cyber Infrastructure in the National Science Foundation. One of the aspects of our contributions today, I think what you'll hear is a fascinating set of developments led by Charlie Catlett, and really is the applications of networking and information technology really to contribute to the very practical value of understanding cities. In this respect, this is an exemplar project across many of the areas that include data and computation and networking and sensors, and information processing and digestion, a lot of things that are really at the core of really is the aspirations, the interests of information technology contributing to contributing practical value to, again, the understanding of cities. So with that, it's my privilege to welcome back my colleague, Charlie Catlett, and learn from him and his basically developments in his Internet of Things efforts, including as led by the University of Chicago, Argonne National Laboratory, and Charlie's own interdisciplinary center in Chicago. So with that, Charlie, it's my privilege to welcome you this morning.
Thank you, Bob.
Before we start, Charlie, this respect is just as a procedural matter. Those of you that have joined us previously or are joining us for the first time, please mute your phones. We know that you're out there, but the piece of basically is because of the constraints on the NSF networking, what we'll do is we will hold our questions to the end, and that way basically we'll have the ample opportunity to learn each of your thoughts. But just as a practical matter, please mute your phones, and we will rejoin you all at the conclusion of Charlie's time with us. So thank you all. Please, Charlie.
Thanks, Bob. So first of all, thank you, everyone, for taking time to hear about what we're doing in Chicago. I'm speaking, as you can see on the title slide here, I'm speaking on behalf of a pretty large team that's come together over the last 5 years or so with a common interest in making cities, Chicago and other cities as well, making cities work better, but starting by trying to understand what the challenges are and what the opportunities are for scientists to get involved with cities and understanding those challenges and then trying to address them. So today I'll take you through really 3 different areas that we're working in that all have to do with different kinds of data. But I want to start with what we've been doing with the city, where we started out, and then some of the motivation behind the Array of Things project. And I'll spend most of my time telling you about the Array of Things because that's most of what I'm doing lately. It's not all that I do, but it's the thing that is on the largest front burner right now. As Bob said, I'm from the University of Chicago and Argonne National Laboratory. I'm actually at the University of Chicago's downtown offices where some of our staff hang out on the Michigan Avenue. You might have seen before the Wrigley Building across the street. Argonne's about 30 miles southwest of where I'm sitting, and the university's 7 or 8 miles straight south along the lakefront from where I am. Let me start by saying I have been thinking about cities for a while, and as a computer scientist, computer engineer, I tend to think about things like resilience. It's not the only thing about cities, but just to use resilience as an example, from the point of view of a technologist or an engineer. And recently, through the Rockefeller 100 Resilient Cities program, there was a kickoff workshop here in Chicago in September where the mayor invited about 120 or so people from all around the city, all walks of life, people from universities, organizations, educators, etc. And the Rockefeller Foundation uses this, what I think is a very interesting framework to think about city resilience that came out of some work that RF did. And each of the 120 people in the room we were broken into teams of about 10 or 12 people. And we spent half the day looking at this framework, and you can see there are 4 major areas, and then within each of those 3 sub-areas, and this rating the city. So deciding across this group of 120 people, where do you think the city of Chicago is? Red being we're in trouble, yellow being we could do a lot better, and green being we're doing fairly well. So when you first think about, or at least when I first thought about working with cities, it was all about the bottom left of infrastructure environment. Turns out that the rating that came out of the 12 groups when they were put together rated that part pretty well. But in the bottom right, the economy and society, those kind of challenges, and then health and well-being on the upper right, those kind of challenges don't directly tie into any of the projects that I did as an undergraduate in computer science or electrical engineering, for example. So part of what we've been doing with data is understanding more where computer science and engineering can help other disciplines with some of these other 3 areas besides the infrastructure environment. So I will talk a little bit about water sensing and things like that, but much of what we've been doing with Array of Things has been driven by a more balanced picture than just the bottom left. When we first started working with the city, and now this has been probably 5 years ago, I was intrigued by Mayor Emanuel saying, I'd love to have some kind of an indicator for neighborhoods that would tell me if they're heading in the right direction or in the wrong direction with respect to things like education or economy or crime or health. So that we started talking about this as a neighborhood health indicator, meaning the health of the neighborhood as an environment, and not necessarily the people in it. And so we began working with the city on a variety of projects looking at their data and trying to make some sense of it. And what we found is what social scientists, of course, have known for a long time, and that is that in any city you have a very different experience living in that city, even if you're just living 5 miles away from someone else. So here are some maps, for example, in the upper left from a group that looked at life expectancy in Chicago. And
Charlie?
Yeah.
Charlie, I apologize, but what we're getting is a lot of chatter through the network on our side of things. If you could please execute *4.
All right, execute order 66, just a second.
Yep.
The conference is now in silent mode.
Okay, so I'm assuming that's okay, and there's maybe some way you can, I won't know if it's not okay because you can't tell me. So again, upper left, life expectancy, the difference between the dark red and the light yellow is 14.6 years in Chicago. The bottom left, a different study, same phenomenon, you have a 20-year span between neighborhoods. In the middle there, you see Chicago neighborhood asthma prevalence. And again, you see these pockets of red, which is 20% or more of incidence of asthma kids there, and green with less than 9%. And at the bottom in the middle is the same sort of study looking at youth hospitalization for asthma in Boston, and you can see that it's very neighborhood specific. And then, a practical matter that most anyone in cities deal with is transportation. On the right is using the Google Trip Planner tool, a color code of the city of Chicago where you can see where it says Chicago, the Chicago Loop there, and that's about where I'm sitting right now. If you live in one of those green areas, it's going to take you 30 minutes or less to get into the loop, into the center of the city there. But if you live in those gray areas, it's going to take you 90 minutes or more. So just moving a few miles in one direction or another, and in terms of scale on this map from top to bottom is about 20 miles, so maybe 15 to 20 miles. So where you are in the city makes a huge difference. And we did some more looking at these kind of neighborhood effects. Here's some work that we did with Brett Goldstein, who's the former Chief Information Officer for the city and Chief Data Officer, Jeffrey Groger, and Maggie King from the U Chicago Harris School. What we wanted to understand was whether we could predict crime more effectively by including changes in weather than we could if we didn't include weather or changes in weather as as a leading indicator. And so we took crime data for several years, eight or so years, across the 866 census tracts for the city of Chicago. That's the resolution you're looking at there. And we first tried to predict crime just based on a very simple looking at the patterns of crime over the previous few years for that place. And we developed a tool that would allow us to slide the slider at the top of the screen out up to 72 hours. And by hour, we predicted the likelihood of 3 different specific types of crime that you see in the lower left: violent crimes, robberies, or assaults, again based on the database of crime records from the city. And then we did the same prediction, and by the way, so red is much, much more likely than the citywide mean and to have a crime of this kind, violent crime shown here, and green is much less likely. And so we then added weather as a leading indicator, and we actually found that the predictions got better, especially when you look at changes in weather, changes in temperature. For example, a quick rise in temperature before a weekend after a long cold period tended to have a noticeable effect across the city. Now the problem is we had crime data with addresses, street addresses, but we only had weather data from NOAA for large areas of the city, just a half dozen or so places. And I know there's weather underground and things like that, but we were looking at weather from NOAA, and the resolutions really didn't match up. And so we started thinking about the need for a higher spatial and temporal resolution of data as a result of that project. Now I'm going to back up just a moment and talk about 3 different kinds of data, and then I'll come back to that sampling issue. We have a project as part of the DOE Exascale program. It's a seed project with 5 labs, folks listed at the bottom there, where we're trying to look at a framework that we could build, and a lot of it is borrowing frameworks from other high-performance computing projects that would enable different kinds of urban models to be coupled together and exchange data from one model to another that would affect how that model runs, and try to capture in that data exchange the interdependencies between things like transportation, climate, weather, building energy use, or social economic systems. And that meant that we had to look at what turns out we think of in terms of 3 different types of data. There's open data, like you see on open data web portals. There's data from sensors, like Array of Things. And then there's protected data, like census data or healthcare or education data. And to really model and understand cities, you often need to pull from all 3 of those areas. We talk about the modeling. I'm not going to go into a lot of detail on how we work with sensitive data. I'll just say we're working with the U.S. Census to build a platform that allows us to manage the workflow for dealing with and sharing sensitive data in a safe way. But in terms of modeling, we started with this project just saying, let's see if we can adapt the building energy models on the left with the urban atmosphere models on the right, and get down to a resolution of that's meaningful inside an urban canyon, where the model on the right, the climate model, is typically run at resolutions at kilometer or more. And we want to get down to maybe 100 square meters. And so that means dividing up in 3 dimensions the space around the buildings in a city like Chicago, and then the building surfaces become the interface between urban atmosphere and the buildings. So we started, just to get started, we started with this part of Chicago that I've highlighted in the middle, partly because some of our funding comes from the MacArthur Foundation, and their building is, I don't know if you can see my pointer, but their building's right here, the Marquette building. And then these buildings at the bottom of that area are federal buildings, the courthouse, and then the federal office building on the left. So we said, let's see what we can do with getting the geometry for those and getting energy data. And then if I blow up in that area there, and then on top of that, getting energy data and building geometries, let's go ahead and put some sensors there on rooftops and on the corners so that we can have, we can actually seed the models and validate the models from measurements. So the idea was then to take that geometry, turn it into a form that the computational models would understand, and then be able to do even just simple models of airflow around those buildings, like you're seeing here, some work from Alex Obabko and Rob Jacob. So then the idea is to scale this up to an entire city, and just the Chicago Loop alone is about 500 buildings, so you don't want to have to pull the geometry in by hand. I'm trying to get to the next slide here. Pull the geometry in by hand, you want to be able to automate that in some fashion. So with these three types of data, then I want to spend a little time on the open data and come back to the frame prediction and things like that. And I won't spend any time again on the sense data, other than just to mention the project with Census that they have a prototype that we just taught some courses at the University of Maryland with. And then that's protected data, sorry. And then sense data I'll talk in some detail. All right, so open data has been around for a while. When we first started looking at open data in Chicago, we found that people were doing things like in the lower left-hand side there, you have color-coded building footprint down below. The mostly green map just up and to the left of that is zoning. And then a snapshot from an animation of a 2-day blizzard where the dots on that map are the snowplows, and the blue areas or blue lines are snowplows dropping a blue dot every time it goes by, so you can watch the movement of snowplows. And these are nice, but they don't really help just in this form. They don't really help the city much to understand maybe, but certainly not to optimize. But that, for example, the GPS data can be used to ask questions like, in Chicago, we changed the algorithm for picking up garbage and went to a different model that was supposed to be more efficient, but we could actually measure that efficiency by looking at the tracks of the garbage trucks, because Chicago has GPS on all their vehicles. And so we could say number of miles driven and average speed, or average number of minutes spent idling and just putting out pollution. And so you can actually do a quantitative examination of that. It turns out prediction is a major theme across a lot of what the city wants to do. And inspections are something that is another common theme. And so what you see in the right here is one of the first projects that the city did with academics like ourselves, where the health department came to the chief data officer, it was Brett Goldstein at the time, and said, we have 15,000 food establishments in the city, grocery stores, restaurants, et cetera, and we have 32 inspectors. Can you help us do a better job of inspecting all of those given the limited resources that we have? And so what Brett and his team did was to just start with a ranking of restaurants by predicting their likelihood of having a food safety violation and just doing a high, medium, low risk assessment. And then on the right, what you see is a 60-day double-blind trial where over that period of time, half of the inspectors were told to go about their business as usual, a random inspection or whatever the inspector decided. He or she had a group of places to visit. The blue line is another group that were given a list without being told why they were given that list. And so they followed the ordered list, going to the high-risk places first. What you see is an average 7.4-day spread there, which is a huge difference. If you think about people in the city being exposed to a food safety violation for a whole week, that's a significant health risk, and food safety is one of the health risks that has a huge impact on the economy as well, people missing work and so forth. So this method now, we've got a team that was set up with some funding from the Bloomberg Foundation, where we've brought together applied mathematicians and data scientists from DePaul University, University of Chicago, Argonne, and University of Illinois at Chicago. And they're working on a regular basis with the Chief Data Officer on problems like this, where they're applying their best, latest tools to some of these challenges like inspection optimization. And what they're trying to do is push that blue line up and to the left, whether that's a food safety inspection or fire inspection or elevator inspection, et cetera. Now here I have just a few minute animation. Bob Chaddock gave us a EAGER award a couple years ago. We said there's a lot of open data out there, but most of the users that are in the social and economic sciences really, they're not aware that it's there, and there's no way to search across multiple sources, and so it's just real, it's sort of like the anonymous FTP servers of the 1980s. So we built this tool that's a geospatial database that pulls in data from all different places and allows you to use a map and a calendar to do a search. So here I've done a search of the area around the University of Chicago, and you can see it's got 22 data sets it's found so far and about 40 shapefiles, shapes of parks and building roads and things like that. And maybe I'm interested in this food safety inspection, so I'm going to go to the food safety inspections data source. And you can see in the lower left I can grab that through an API. In the upper right I've got spatial density, and the lower right I've got some indication of temporal signal there. I take the resolution down to 100 meters, I kind of zoom in on the university, and now I really want to know which of these inspections was based on a complaint. So not just a routine inspection, but somebody actually complained of food poisoning, or maybe they complained that they saw a food safety violation visually. So I can then add that because we've got the data in the geospatial database, and I can add that and filter down on just those restaurants that were inspected because of a food safety violation. And then I can download this data in various forms. So the purpose of this tool was to, first of all, allow people to explore what's available with open data, and then to examine it at this high level, after which they would download the data and go off and use whatever workflow or data analyst analysis tool that they would want to use. Now what I just showed you was actually a portal that we developed named after the geospatial database Planario, but it uses all of Planario's APIs. And the city subsequently built this portal that I'm showing now. It's called OpenGrid.io, and they use the same backend database and APIs to build a portal that you see that's not aimed at social and economic scientists or policymakers like ours, but it's aimed at residents. And so it allows residents to explore the open data from the city of Chicago. Now, if I go back to this, as I mentioned before, how do we get the kind of resolution data that we need if we don't start putting in different kinds of measurement systems? So let me talk about sense data and what we're trying to do with the array of things. And I'll say Planario, what I just showed you, has been augmented with APIs for sensor data, and so that's where the community will be able to get all of the sensor data from Array of Things, and they'll be able to get it with the portal or with the APIs. They can write applications that will draw on the data. So I talked about weather in the previous slide. On the left-hand side, you see these huge tens of square miles, 30, 40, 50 square miles in some cases, of parts of the city where we have no information about air quality because air quality sensors are traditionally very expensive to the sensors themselves and expensive to put them in. So when we thought we might have the opportunity to work with the city to put sensors around the city, this has been a couple years ago now, we started having workshops with different science communities and asking them the question, if you could place devices throughout a major city like Chicago, what would you want to measure? And from those different workshops over the course of 2 or 3 years, we ended up with 4 teams that you can see there, each of which is led by a scientist, one of the co-investigators of the Array of Things Major Research Instrumentation Award from from NSF. And so those communities really informed us of the capabilities that we needed to provide for the array of things. When we got to the social sciences, actually, that's when we started thinking maybe we would need cameras. We already felt that we needed computation out in the device, and I'll talk more about why and what we did there. But the fact that we have cameras and a microphone and embedded computing so that we can run machine learning codes means that you could imagine at an intersection that you don't just count the vehicles and the pedestrians going by, but you actually might be able to capture near misses, a car skidding to a halt, a pedestrian having to run out of the way of a truck, etc. And this is important as we learned from talking to the city for traffic safety. There are many cities, DC and Chicago among them, that have this Vision Zero program. In Chicago, it's 10 different departments and agencies working together with the goal of eliminating traffic-related fatalities by the year 2022. That's a safety program, and safety programs need to have near misses, not just the accidents. So in Chicago, by the way, there are about 150 people that are killed in traffic-related accidents. It could be a biker, a pedestrian, or somebody in a car. So this is also a data science problem. They take all the data they have and try to look for common factors, both at the intersection or the roadway or in the behavior of the people involved. So once you start putting machine learning out there in the camera, you can start doing some interesting things, whether it's looking for standing water or flooding, looking at crowds of pedestrians and vehicles, or in the upper right's a project that we were asked by the Cook County Forest Preserve if we might be able to, or maybe it was the Botanic Garden. There's a particular kind of frog that only makes a sound once a year when certain things are happening once a year, and they don't want to send somebody out with a clipboard listening for that sound. They don't want to record an entire year's worth of sound. So maybe they can put a microphone out there and use machine learning to look for that particular sound signature. Now in this, I'll just mention that NSF's also funded a project called the Sounds of New York City, or Sonic. That's Juan Bello at NYU, and we've been working with Juan because he's done some amazing work with using machine learning to identify the sources and the types of sounds that are in the urban soundscape. So this, in addition to machine learning folks like Nicola Ferrier at Argonne, who do image processing. In the upper left, I'll mention the lower right as well. There are groups around the world that are doing this kind of computer vision-based flood detection, or even classifying fish with underwater cameras. The NCHC in Taiwan has done some great work there, and we hope to borrow some of their code in our devices. So part of what we're doing with the Array of Things is this notion of putting parallel computing as an open platform so people can write classifiers and push them out to the nodes, and even do some, ideally some deep learning out there to start detecting things like anomalous conditions or events. You see a stylized picture on the left. That's a sample image of, stylized image of what's available from an Array of Things node. They're about 20 feet up. We stylized the image because our privacy policy, we've got a little bit over-aggressive. We'll have to address that, in that we prevented anyone, including ourselves, from publishing any of the images. So it's a 5K or 5 megapixel camera, so obviously it's going to be a much clearer image than you see there, where we could see the kind of vehicle. We can see cars or bicycles, and can even get to the resolution where you could detect whether someone's wearing a helmet or not, for example, on a bicycle. So this whole idea of using these cameras and microphones to observe the city, we've been starting to think more about in this collaboration I mentioned with Juan Bello at NYU and the Array of Things and Sonic project, to say, let's begin to interact much more in a much more directed way with the social scientists, to say, and we've been now asking social scientists, if you could be like William White with a recording of a public space, or put a student out there with a clipboard, what kind of things would you be looking for? And can we translate those and we've been calling them automated observations. Can we translate those into some form of computer perception, sound, images, even other sensors, so that we could use the array of things to not just count the pedestrians, but also to look at the use of public spaces, for example, the average size of groups or the stickiness of a place, whether you see people walking dogs or babies or families or you just see adults there. So the idea behind that machine learning down on the device is to turn the array of things into a sort of, robot version of William White or his graduate students. The other advantage to this when it comes to privacy and as well as cost is that this means that from a privacy point of view, we can extract the information we want from the image without having to store the image. Not having to store the image means we don't have to transmit it over, we're using cellular communications. It means we don't have to transfer it over networks at least some cost, would add up over time. So it allows us to have a very precise set of privacy policies, which, by the way, we developed with public interaction. Public meetings are out on the website now. You can go to the Array of Things website and see them. So the Array of Things, let me kind of turn to the hardcore computer engineering and sensor part of things. As most of you, any of you have done electronics or computer science know, it's a fairly straightforward thing to build a temperature or humidity sensor or weather station. They're pretty low cost. On the upper left here, you see a board that we designed with a simple processor, very reliable, not remotely programmable very easily, and a set of off-the-shelf sensors. And you put that together, it's a very reliable system with a modem of some kind and send the data up to the cloud. You can put a sensor network in at very low cost, very reliable, because you want it to run for a couple of years before before you have to go out and replace it. When we added machine learning, we added Linux devices on the nodes. That meant that we had a device that is not so reliable, at least in terms of being able to run for a couple of years. So we had to sacrifice reliability for the sake of programmability and to allow the science community to be able to download new kernels, new libraries, or what we expect we will settle on is the downloading virtual containers of software. So you want that programmability, but you can't really live with the unreliability of a programmable computer if you're putting stuff up on 20 feet up on a pole in a city. So we had to work very hard at reliability. I'll come back to that. My slides are a bit out of order here. So the idea then was to put that computation on there to run the environment, the libraries, the frameworks, the operating system that the science community uses, not some proprietary system from a vendor, to put novel sensors in place, so a modular hardware and software design, and take advantage of these new low-power CPUs. So with reliability, what we ended up with is two Linux devices, one of which this is an early version of the supervisor board on the right, one of which is bolted on top with a slightly different arrangement on that board. So the 4-core ARM processor on the left, these are both from a company called Odroid. And among the reasons, probably the primary reason we chose this particular platform for this first round of design is that these have two hardware boot media. So they're micro SD like all of these class of devices have, but also an eMMC memory card. And so that would give us extra reliability. We can recover from a soft error by booting from a different area on the primary boot media. And recover from a hard error by booting from a known good image, boot image on the secondary memory. The one on the right, the 4-core ARM with an 8-core GPU, is the one that the cameras and microphone are plugged into directly. The one on the left is doing all of the housekeeping for the node, which is communication, implementing security protocols, etc. So we ended up with this device on the right that has things like heartbeat monitors, a 25 hertz signal that the control processor, again, a very reliable but not easily remotely programmable. We can actually upgrade its firmware from the Linux devices, but you got that very reliable processor. It's watching the other devices in the enclosure. It's watching their temperature. It's watching the temperature inside the enclosure, even the humidity inside the enclosure. In the middle there, it's monitoring the current that's being drawn. And so it has the ability, it being this small microprocessor on the supervisor board, to gracefully shut down or reboot the devices on the left-hand side. So we went with the supervisor board and built into that all of the reliability and resilience that we needed. And I'll say, for those of you who've built hardware before, every time you do the whack-a-mole with reliability, you're also adding complexity. So we've had to debug the complexity of the devices as well. So there's there's no free reliability. It comes with some complexity, which in turn affects reliability. Again, this is down on the website, but from those science workshops in interaction with the science community, we ended up with this particular set of sensors for the first round of the first probably 150 to 200 devices that we build and deploy. Now, this is all of the components with the exception that I don't have the microphone showing here. The microphone's about the size of a small cigar. But you can see we've built a couple of boards, two on the left there. You can see the supervisor we call the Waggle manager for the Waggle node, the Wagman. The upper left, our board that's got off-the-shelf temperature, humidity, barometric pressure, vibration, magnetic field, etc. The upper right is a board that has electrochemical gas sensors. We're doing 7 different gases, and that's a board that has sensors from a relatively small company with some disruptive technology, in a board designed for us by Intel. I should back up. Actually, they originally designed the board for one of the Global Cities Team Challenge groups in Portland, for Portland State and John Fink there and the city of Portland. And through the GCTC, the US Ignite NIST, through that set of interactions that they supported through the Global Cities Team Challenge, we met the people in Portland, and it turned out they were working with people we knew at Intel. And so we've been working with Intel on this board. They've already redesigned it once for us, and we're going through a third design to make them in much higher quantity now. And then this comes back to Portland because we're sending 3 nodes to Portland in a couple of weeks because they want to use image processing. Of course, they want the air quality, but they're also interested in their concern and whether this concern is valid or not. They're concerned that people riding bike share bikes are less likely to wear helmets than people riding their own bikes. And so the way they want to look at that is by using machine learning to image process, count the bikes, decide which one's the bright red Portland bike share or the private bike, and then for each of those determine whether the rider's wearing a helmet. So they want to gather statistics that you really can't go, to Mouser Electronics and buy a, bike rider with helmet detector that you can put on a computer board. It's the other thing that's not showing here is our particle sensor. We have an AlphaSense device that we use. It does PM 2.5 and PM 10 in its native form, or 10 and 2.5 microns. And again, actually, also through the US Ignite people, Glenn Reichert introduced me to David Larry at the University of Texas in Dallas, who was working with AlphaSense to modify the firmware so that it gives a histogram from 1 to 100 microns, which means we get the ultrafine even below PM 2.5, but we also get pollen, which tends to be in the 20 to 60 or 80 micron regime. So it turned out through Dave Larry's work at the University of Texas, Dallas, we got a better particle sensor, and what David decided was he'd rather use our reliable platform than continue to develop his own. So we actually have Waggle nodes on rooftops down in Chattanooga, Tennessee, where David's doing an NSF-funded asthma project. So Again, not shown here is that particle sensor. Other things that we did, so here you see the packaging. In the left-hand side, the thing that says Array of Things on it is all of the electronics in a waterproof aluminum box that you see in the bottom left. You can kind of see that we take these Odroids and we buy them without heat sinks so that we could put these aluminum ingots on that microprocessor. There's another one that the other Odroid is mounted underneath the supervisor board, and those are when the box is closed. There's a little bit of heat paste on the top of each of those ingots of aluminum for each of the Linux devices, and then we're using passive cooling, essentially trying to draw heat out of the microprocessor and into the aluminum box. And I'll say, one of the lessons we learned is that this 3D puzzle is quite challenging for a couple of reasons. One, because of the supervisory functions, we ended up with a lot of connections, serial lines, etc., thermistors inside that box that make assembly complicated. The other is if you want to do what we're doing, which is where it's foam loaded, so it's a kind of a springy when it closes, but tolerances are really important. Some of the first units, somehow the spec for the aluminum heatsink was off by 2 millimeters. It doesn't sound like much, but when then they screwed the box closed, it was putting 25 pounds of pressure on the microprocessor. We didn't find out that this was a problem until a few weeks after we put the first 6 of them up, and 3 of them we think, we're going to do some post-mortem hopefully next week, 3 of them we think failed because of that stress on the microprocessors. And then in this Stevens shield that we designed, this injection molded stack of upside-down bowls, has a cavity inside, and this harness with sensors is sitting in that cavity. You can see the camera in the lower left of that where those 8-pin connectors come in. You can now see the microphone, the black. The gas sensor on the back side is now covered with a Faraday cage, and then this black with an orange stripe is the particle sensor. And then on the right-hand side of that harness, you see that what we call AirSense, that board with the off-the-shelf sensors. You can see what it looks like in the upper right there. Right above, I'll just mention, right above an ominous pan and zoom surveillance camera whose privacy policies are unknown to us. Ours, on the other hand, are published. But our camera, I don't know if I see my image there. I don't know if I'm in the way, so I'm going to move my image down. So you can see the window on the bottom where the camera points down to the road surface. There's another camera on the top of the blue enclosure pointed straight up, along with an infrared and ultraviolet sensors, and that is for our weather and climate research partners. We started working with the City of Chicago electricians a little over 2.5 years ago. We came to them with an early mock-up, and we said, hey, can you work with us to make sure that, for example, this doesn't electrocute anyone if it fills with water or something happens and you guys are trying to change it out? How do we do electric safety? Do we put fuses in there, et cetera? And second, we wanted to make the mounting of this, once the wiring is done, because these are wired to a dedicated circuit. You can see the yellow loop at the bottom with the power. We wanted, once that wiring to be done, for the swapping out, for an upgrade or a repair, swapping out one of these to be as quick as swapping out a holiday decoration, which they, of course, do routinely. And so you can see there are 2 stainless steel straps that hold this to the pole, same stainless steel straps used for other devices, including the street sign, walk, and street signal lights. So when we want to replace this and upgrade it, or something goes wrong, a person goes up in a bucket truck, unplugs the existing one. It's a screw-on NEMA-rated waterproof connector, snips those 2 stainless steel bands, and then puts the new one up in 10 to 15 minutes. And as you know, we learned that the phrase "time is money" really starts to get the rubber really meets the road when you're dealing with union electricians and crews of 3 with a bucket truck, et cetera. So I tell people a rule of thumb is about $10 a minute for one of those crews. We were really fortunate in the city of Chicago. The city is very interested in this data to be able to do proactive policy rather than just reacting, or worse yet, using people as sensors for bad, harmful gases and pollution. And because of that, the city is doing all of the installation for these at no cost to the project. That's about a 2.5 to 3 hour job to do the initial wiring. You open up the traffic control box that's down at the sidewalk, tie into a breaker, go through a conduit under the sidewalk to the pole you want, or actually to a manhole, and from the manhole to whichever pole you want, and then they go up, they drill a hole, they drop these come with a 35-foot whip, that yellow cable, they drop it down, they strap it on, plug it in, and then splice it at the bottom of the pole. So that's a 2.5 to 3 hour job. The city's pre-wired about 40 intersections for us so far, so they're actually way out in front of us. And I'll also say this has been, so we now have met with and have enthusiastic support with 7 different layers of management in the city of Chicago. I tried for my networking friends to figure out a way to make it 9, but it's about 7 layers, from the electricians that go up in the bucket truck all the way up to the deputy mayor and to the mayor. As a sign to us that we really had reached a collaboration point with the city that we were aspiring for, after one of the groups went out to do wiring, they came back and said, hey, we went to this intersection and you wanted your device on this particular pole on the southwest side of the intersection, but you must have been looking at Google Street View from the winter, because when we looked up, we thought there's a tree there that's going to block your upward-facing camera. So we hope you are okay that we moved your location across to the other side of the intersection. So even how the electricians are so excited about the project that they're optimizing for us, which was very gratifying. A little bit about the overall architecture. These we're using encrypted cellular communications. AT&T is our partner here. And the data goes into a queue. There's raw data, which is like the sensor readings, the voltage levels or current levels from the sensor. And then we do the transformation, the calibration, et cetera, to transform that data from a voltage reading to a parts per billion or temperature Celsius, et cetera. And then we have that process data inside what we call Beehive, is the mothership. And then we push the data up to Planario, where we've got sockets for streaming, portals that people can build, including the one we've already built, and including the city of Chicago's Open Grid. So once we're pushing data out into Planario, it's automatically going out into these other portals, and then APIs for developing applications. At the bottom there you see there's also control traffic, where we would keep configurations and do the management of this. And so you can sort of think of Beehive, especially the control part, as the head node to a compute cluster or parallel machine, with the difference, of course, being that the devices are geographically spread around. The bandwidth is not the same as you have inside a machine room. You don't typically upgrade them all at once like you might with a compute cluster. We're going to roll the 500 as part of the MRI award, 500 over the next few years. We'll roll those out in waves so that we have these launch windows where we can insert new hardware, and then we'll have to manage configurations to help the science community be able to take over, say, 100 nodes and test out some software before we push it out to more nodes. This doesn't add any, I guess, real information content, but it's fun to watch. This is a time lapse of assembling one of these devices, and you can see already there's a lot of moving parts, well, not moving parts, a lot of components, a lot of connectors. We've spent the last 5 months with a third party to do this assembly, to do the translation between having the people who invented it build them to having somebody who doesn't understand it build them. And that means that the test codes and the procedures have to be really mapped out in a much more rigorous way than you'd have to do in-house. I mentioned working with the City of Chicago electricians. You see in the bottom a couple of pictures of the guys we work with. And then in the left-hand side are the first 40 nodes, 40 locations, all of which, with the exception of 2 or 3, have already been already been wired up and ready for us. There are 9 devices up right now, plus a few at the University of Chicago, one at Northern Illinois, one in Denver, one in Seattle. So we this spring are going to hope to finish these 40 and then get another 60 out there. There's 60 locations that are going through review right now. What I want to point out is that this is doing science in the public way. So unlike a compute cluster or a microphone or microscope in an office or a laboratory, we're touching people where they live. And that means we can't just, well, I suppose we could just put these things up and not say anything, but we felt it was important for the success of the project for the residents to be involved, and obviously we're already involved with the science community and with government. And so what you see in the left-hand side is the methodology for placing these 500 sensors around the city, where we want to support specific science questions that start with some concern of residents or local businesses. Might be air quality, like you see in the southwest side here. It might be traffic, like you see in the loop, or pedestrian safety, or it might be the lake effect, these ones along the lakefront, and then this transect that goes in. Might be the lake effect for weather and air quality, and then a few notes here that look at new parks, bike lanes, running tracks, et cetera, where we have some interest in understanding their impact on neighborhoods. But again, we start with something that the residents of the city are concerned about: safety, traffic safety, air quality, noise, et cetera. Make sure we can find a science community that, if we provide the data, would actually want to analyze it, and then someone in government, a department head or a commissioner, who is eager to get that insight from the science community and try to do something about that concern. We've been able to make this with companies in the Chicago area. There's another 5th company that's in Minneapolis that we've used for some of the bent metal. But this was important not just politically, and obviously it's always good if you get support of the city to make jobs in their neighborhood, in their city and area, but also turns out for this stage of a project where you're taking something from prototype to phase 1 to the next phase and improving it over time, you really want your manufacturing partners to be within an hour or so drive of your engineers. So it may be, I'm not convinced it is, but it may be a little bit more expensive, for example, to do the injection molding out by O'Hare Airport than it would be in southern China or somewhere like that. But if you factor in not having to send engineers over for a week to debug something, maybe the cost actually starts to even out. We've also been working with local architecture firms and artists to try to apply the data in ways that a normal person walking down the street might be able to engage. This is the Bloomingdale Trail, or the 606, an elevated track that's been converted like the High Line in New York. There's a bridge on it, and there's an art group that's been working with the Public Land Commission. They have these LEDs on the bridge that are right now color-coded by temperature, but they are planning to use our APIs to color code by air quality and other factors. There'll be a node about 2 blocks away from this bridge, and then we're planning to put nodes along the 606s as well. And then I also mentioned we've worked with Lane Tech High School on the northwest side of the city. It's a college prep school with about 4,000 students, and starting last year we did a 8-week curriculum where groups of kids like this, three kids in a group, 150 kids total in 5 different sections, took this curriculum where they started with, here's a menu of sensors that you could use. Do you have a question about your environment of your school or activities in the school that you might want to ask? And then let's translate that question into a sensor device where you learn how to wire it up and program the little Arduino compatible, it's called a photon, and then you decide on your enclosure and build the enclosure in the makerspace, deploy it, collect data for a week, and then analyze data for a week. These are students from last year, 150 kids. Just 2 weeks ago, we started this program a second time. It's funded by the Motorola Foundation, and we've got colleagues at the School of the Art Institute working with us. Second time, 160 kids involved. Last year, because of just some curriculum prerequisite errors in retrospect from the point of view of the faculty members. We didn't have the participation of young women that we had hoped for, but this year they were able to fix that curriculum to not inadvertently leave people out that hadn't learned how to use, say, the CNC machine or laser cutter, and teach that as part of the course. So this year, about a third of those students are young women, and we're going to continue to push that. And of course, many of them are minorities, a very diverse school there. I'll just close by saying we've been surprised, and this is one of the reasons we took this 5-month hiatus, delay, whatever we want to call it, to transition to manufacturer before we were planning to. We'd hoped to go through this first phase, building them ourselves and then optimizing that design of assembly. We pushed because we've now had over 75 requests for devices, for partnerships, for pilots from around the world. And so we're trying to capitalize on that interest because it gives us an opportunity to help universities in other cities do similar projects with their cities. So the model for these pilot or other projects is we don't do a pilot project unless there's a local university that's interested in working with us and working with their local city. So that's a prerequisite, for example. In Denver, we started working with them a little bit before we figured out we needed to have a university partner, but they're pulling in Colorado. I guess it's Colorado State or University of Colorado. It's Panasonic that we've been working with there. But in Seattle, you can see that's Bill Howe at the University of Washington, and then Mike Mattmiller is the CTO there. So our rubric here is we want to support a local university that wants to do a deployment. Most of them have said we're very happy for our devices to come as turnkey and send the data back to your systems in Chicago, and we'll use the APIs to pull our data out. So that becomes a tremendous opportunity for people studying cities. We can actually get a footprint like this out there, pulling in similar measurements from cities of various sizes, climates, cultures, geographies, topologies, etc. And what we're trying to do now is say, well, this is great. A lot of cities will do Array of Things. But there are really interesting sensor projects. I've already mentioned Sonic. CMU guys are doing amazing things with Pittsburgh. Georgia Tech with Atlanta. Several universities in the D.C. area, Stanford, et cetera, are doing work with their cities with different sensor platforms. So we've begun the conversation with some of these others and with commercial providers to say, can we just take advantage of the 30 years of sensor networks that have been done outside of cities to try to move to the point where that global information library of urban data can have data in it from a variety of different sensor platforms, not just Array of Things, and be stored and represented with data and metadata in a way that a scientist doesn't have to do the mapping or interpreting of what temperature means here or pedestrian count means over there, where they can pull that data together. I'm going to stop there. I should have asked how long I should take, but we're right at just almost the top of the hour, so I'm going to stop there. And I'm hitting *4 here so that we will all be able to hear the announcements in airports and the traffic.
The conference is now in talk mode.
So I've turned this into talk mode. I'm happy to take questions. I'm sure there are things that I forgot to cover, and so.
So thank you, Charlie. Again, on behalf of the